So today we start our topic on complex trig functions and more of the complex logarithm. And well, I don't think we'll get here today, but the goal eventually is to get to complex powers. That is, take the complex power of a complex number. Right? So you start with some complex number, like what's a good complex number?
A plus bi.
A plus bi. Well, that's something that's so like abstract. How about I? Right? And you want to raise it to some complex number, like 3 minus 2i, or to just to I, right? Okay, that's a I. You should be able to define something like that, right? Okay, so we'll end up defining something. Okay, but before we get there, let's start with some.
Wait, I'm sorry, I missed something. So the research topics, those are on the internet.
They are. Yeah, they are.
Okay, so there's like a list. There's like
the double quotes.
how am I gonna find this? It just says.
Go to our
research topics?
webpage, and there'll be this big thing that says Final Project Page, and you click on that,
Okay.
and then there'll be this big thing that says Final Project Topic Ideas.
When is the final project due? And is it instead of a final exam?
No, certainly not instead of a final exam.
How big can the groups be?
3.
Up to 3. No more than.
We can't all work together and do
No,
final
no. Yeah, but when you have, here's the thing, when there are multiple people in a group, you have to still do the work of multiple people. All right, so it's not like, oh, here's one person by himself does a 7-minute talk, and then the two people
So the
work
3
together
people
and
have
do
to
the
do
same
a
work.
15-minute talk.
It's not so much the length, but the length will be longer,
Level of
and
content.
the content should be
Content
much
will be
deeper.
short, okay.
Yeah.
So we pick one topic to split 3 areas or 2 areas of that topic?
Split it up how you want.
No, well, I'll let you
You write
guys.
the A.
You guys can
write
figure
the
out what
plus,
you want to do
I
and
write
run
the
it by
BI.
me.
Yes, I get the plus.
Okay,
Fine,
so
the application.
let's quickly review just what we know. So first, we define a limit. Right? We said something like limit as delta z goes to 0 of f of z plus delta z minus f of z over delta z. And this is the derivative of a function at a point. And if this limit exists, then the function is differentiable at the point. Okay, so if this exists, f is differentiable at z. Now, we had another word which means differentiable, and it was analytic, but it means a little bit more than differentiable. What's the difference? It has to be
Open set.
exactly right. You're not just differentiable at the point. It has to be differentiable in an open set. So f is analytic at z if f is differentiable in an open set containing. Fine. Then we proved that a necessary condition for a function be analytic at a point was that it satisfied the Cauchy-Riemann equations. And so these took the point of view that, well, if your function can be written in terms of two functions of two real variables, u and v. Right, so here u is a function of x, y, and v is a function of x and y. The Cauchy-Riemann equations say that the partial of u with respect to x should equal the partial of v with respect to y, and the partial of u with respect to y should be the opposite, the negation of partial of v with respect to x. Now this was a necessary but not sufficient condition for a function to be analytic at a point. Right? For the function to actually be analytic, you required that u and v be continuous, that all their partials be continuous, and the Cauchy-Riemann equations should hold. And if all these hold, then f is analytic, right? At whatever point z you're talking about. And you might remember that we took these first two conditions and actually just said that this means that u and v are C1 functions of R2. C1 meant they're continuous, and then they have a continuous first derivative, partial derivatives. Then we said that, well, sometimes it's not nice writing it in this rectangular form. There's also the polar form that you might write your function. So your function might look like this. So here now u is a function r and theta, so it's coming from the polar form. And when that was the case, then instead of having curve, you had crowd. Okay, so this was the Cauchy-Riemanns for polar. And in this case, you ended up getting that the partial of u with respect to r is 1 over r times the partial of v with respect to theta. And the partial of u with respect to theta is negative 1 over r times the partial of v with respect to r. Hope I got that right. I didn't write it down.
Yes, I did.
No, I did it backwards, didn't I? No. Yeah, swap these. There we go. I think that's what we should double check. Okay. Fine. Now, when we proved the Cauchy-Riemann equations, the way we did it was by taking the derivative first along the x-axis and then along the y-axis. And in the process of doing that, we were actually able to obtain formulas. So if we go back to x being given by two functions in rectangular coordinates, then the derivative of f can be written as, well, the partial derivative of u with respect to x times the partial derivative of v with respect to x times I. Now this looks a little strange because it only seems to have x's. But remember, this is exactly how this is exactly the answer we got when we took the derivative along the x-axis. Okay? Now, when you take it along the y-axis, what did you get? You ended up getting that the partial of v with respect to y was the real part, and then you got minus uxi, right? Or uyy. The partial of u with respect to y times I. And since these have to be the same, well, you just look at that. Ux equals vy. That's the first line of Cauchy-Riemann. Imaginary parts have to be the same. Vx equals negative uy. Okay. We proved this in the course of deriving the Cauchy-Riemann equations. Sometimes it will be useful to know this, though, by itself. So you want to take a derivative and your function is given in this way. Maybe you don't have z's lying around. You just have it in terms of functions of x and y. Then it's useful to be able to do this. Okay. All right, so, okay, and then the last thing that we want to remember is that, so if you are in rectangular coordinates, we have this e to the z, and we can write it, remember, as e to the x plus yi, and break this up as e to the x times e to the yi. And we even know how to write this e to the yi, which, by the way, what's the norm of e to the yi? Every single time, right? That's 1. This lives on the unit circle. So this equals e to the x times cosine of y plus I sine of y. So e to the x cis y. All right. So, well, I just said sometimes it's nicer to, if you have this format, you can take the derivative by doing this. Well, let's actually try that here. Well, if I multiply this e to the x in, you should get e to the x cosine of y plus e to the x, and then write sine of y times I. So this here is my u of xy, and the e to the x sine of y is my v of xy. And so if I want to compute the derivative of e to the z, the formula directly to my right says you take the partial with respect to x, and that'll be your real term. So the real term will be the partial of this with respect to x. Yeah, it's exactly the same thing, right? That's just a constant. That's e to the x, no problem. E to the x cosine of y. And then I'm supposed to take the partial with respect to x of the v. Same thing happens. So it's exactly the same thing I started with. So the derivative of v to the z, e to the z. No, that's good, right? Everything is right in the world. It was the indestructible function over the reals. It is still the indestructible function over the complexes. Now, what if we had done it with respect to y, used the second formula? Would it have still worked?
Yes.
Well, it should. It better. Let's test it. With respect to y, this becomes, let's see, negative sine of y e to the x. Is that right? I'll put the e to the x out front. And then minus, okay, we're supposed to do, oh no, we did this wrong, right? We're supposed to do the v's first. Okay, so let's do the v's first. The v first is this part. So the derivative of that is going to be I, e to the x cosine of y, minus, and now we can put in our minus e to the x sine of y, which will become a plus e to the x sine of y times I. Oh, good. That's what we want. C to the z. Cool. So it works both ways. Of course, we knew it should work out because we actually tested the Cauchy-Riemann equations for e to the z last week. And when we did that, well, it matched up. Right? Of course, that matching up just means exactly these two derivatives could do the same thing. Okay, so we know the derivative of e to the z is e to the z. This is very good. So now we want to define sine and cosine for these z's. Right? We've already seen if you do e to the yi, you can break it up nicely in terms of sine and cosine. But when we did that, well, two things. One, it showed that there is an intimate, like, you know what I'm talking about, intimate connection between e to the z, right, and then cosine and sine, right? So the exponential function cosine and sine, there you don't see one without the other, right? But when we did it, we didn't have to put a complex number in here. This is, I mean, y is just a real number. We'd like to know what happens if we want to put complex numbers.
Does it involve the world exploding?
I hope not. I hope not.
You never know.
Perhaps explode. Okay. Now, we already we already proved a formula, but let's go through this derivation quickly. If you take e to the I theta plus e to the minus I theta over 2I, remember what this works out to be?
Sine, something like that?
Close. It's the other one.
Cosine?
Well, let's see. We can work it out just from the definition here that e to the I theta, right, is cis theta. So this is cis theta and this is cis minus theta. So this is cosine theta plus I sine theta. Okay, that's the first bit. Plus cosine of minus theta plus I sine of minus theta. And then you divide by 2I. You say, okay, let's see. Now cosine of theta and cosine of minus theta, those are actually the same thing, right? Because cosine is an even function, so that minus doesn't hurt anything. So cosine theta and cosine theta, they're just the same deal. So you have two cosine of thetas. But sine is an odd function, so that minus on the inside over here can actually be pulled out. When you pull it out, you get I sine theta minus I sine theta. They go away. Did I? Oh, I put an I here. There should be no I. Okay, good. It's going to work now. So the signs cancel, and then we divide by 2, and we get cosine of theta.
Oh, that's a 2?
Oh, what is that number? It looks like a real product.
I thought that was
Sorry, my son gets mad at me when I draw my 2's this way. He says that's not right. 2's are supposed to be like that.
Oh, I like that.
I like the loop.
I was taught this way, and at some point, I think it was a girl in maybe 4th grade or something, or maybe 5th grade, taught me this, and I started doing it, and now I go back and forth in between.
Yeah, I actually do too.
It's kind of rotten.
The loop looks more elegant though.
I like the loop.
I do like a pointy one, like I like the loop because it's easy on it. It's not
Now-
a loop, but it's not straight on the bottom. It's kind of goes on the bottom.
Now this is where the I should be. If we do with a minus in the middle, well, actually everything's just the same, but there's a minus. So now the cosine of theta, you now get a minus cosine of theta, so those would cancel. You get an I sine theta, and remember this became a minus that, so there's 2 minuses, so it's a plus, so you get 2I sine of theta, divided by 2I, and so you just get sine of theta. Okay.
Did we do this already?
We did this already. We really did. Does it feel familiar? Yeah, it's because we did it already. Yeah, it's okay. I even without having read this book yet on how to be a better teacher, I already believe that repetition is an important part of learning. Okay. So on the right-hand side, you have real functions. Sine and cosine you could deal with before you got into a complex analysis class. Right? You've been dealing with those for quite a while. On the left side, you have 2 functions that certainly involve complex numbers. This suggests a possible way to refine the definitions of sine and cosine so that they don't have to eat real entries. We're going to replace what's in the inside by a complex number. And on this side, it looks really hard to do that because you have no idea what in the world does it mean, sine of I. But on the left-hand side, there's already complex numbers, so nobody's going to notice if you add some more. Okay. So, what would be the right thing to add? Right? How are we to write this? Okay, so let's guess. Guessing is always good.
Say so.
All right, so what if I wanted to write down a definition for the sine of z? Actually, let's do cosine, because then we don't have to worry about this tricky 2i on the bottom. Just cosine somehow easier. So I want to define this. This is not a question of what is it actually equal. We get to define it the way we want to define it. But we better define it right, or things won't work. So the cosine up here corresponded to this e to the I theta. So here you have a theta, and it gets matched over here with theta. Everything else has nothing to do with anything. It's just constant. There's this theta. So what maybe could you put instead of theta?
Z.
Sure, z. Let's try. You know, it's a good thing that I put lines on my z's, crossbars.
I do too, actually.
Otherwise, you wouldn't be able to tell the difference between my z's and my 2's.
Yeah. That's why you need the loop.
And you know, the funny thing is, in elementary school, that was considered like the girly way to write the 2.
Really?
Oh yeah, yeah. It was two things. There was the loop on the 2, and then there was the smiley face, or what was it, on the I or something? What did you do?
A heart.
Maybe it was a heart. That's what it was, not a smiley face.
Or
heart.
just a circle.
Yeah, that's right. Some girls did do this, that little thing. Yeah, and it was and when I started doing these 2's, I got made fun of quite a bit.
Oh, really?
That I showed them. All right.
I mean, you can do neither and still have a nice 2. That's what. Want to see it?
All right, now.
Yeah, but that's like half a loop anyways over there. Oh, yeah, it's pretty close.
Instead of doing straight and bound.
How should we define sine of z? Well, okay.
Why not the same way?
Kind of a stupid thing, right? Fine. Okay, now here's the real question. How do we know if we have the right definition?
Let's try it.
Try what, though?
I don't know.
So, let me suggest one possible idea. One really nice thing about calculus is that you get to see that sine and cosine are intimately connected in a very specific way. And like, how do you
They
get?
have to equal 1.
Of course, when you square them,
Squares.
they end up equaling 1.
But the derivative of sine is cosine.
The derivative of sine is cosine. That's the calculus answer, right? What's the connection between sine and cosine? Well, the derivative of sine is cosine, right?
And sine squared plus cosine squared is 1.
That's of course the pre-calculus way to identify. Okay, so let's test both of those.
All right.
Let's see if one of them works. So let's try to do the derivative of sine.
Okay.
So okay, so let's see here. So you have to, well, it's a constant, so that comes out. So 1 over 2i times. All right, so the derivative of e to the iz. Just use the chain rule here. It's I e to the iz. Right? So we know the derivative of the z is e to the z, and we know the chain rule will work. So, okay, and then you have a minus. Minus becomes a plus. I d to the I. No,
Negative.
Minus
negative.
size.
Well, let's see. We start with a minus.
You multiply by the 1.
You multiply.
Oh, but
by
we
the
need
negative.
that minus up there.
That
Yeah,
minus.
yeah, that minus for sure. Yeah, there we go. That makes it look right. Okay, so
Oh wow, it's cosine.
look at that. The i's cancel, and so you're left with e to the iz plus e to the minus iz 2, which is cosine. Cool. Okay, but it should work the other way around, right? If you take the derivative of cosine,
Keep it
Minus sign.
you should get minus sign. So let's double check that. So we can pull the 1/2 out, and again you get derivative is I e to the I z, and then it becomes minus I e to the minus I z. Okay, so you can pull the I out, and you get I over 2 times e to the I z minus e to the minus I z. But the answer should be, well, it should be over 2i. And actually, it should be an extra minus, right? It shouldn't be just sign, it should be negative sign.
Well, 1 over I is the same as negative I.
That's right. That's right.
So, going backwards, I is the same as negative 1 over I.
Precisely, right? I is really easy to move up and down. Because, as Christina pointed out, 1 over I equals minus I. Remember, there's a couple ways to show that. One is you can say, okay, we'll just multiply top and bottom by I. You get I over I squared, which is I over minus 1, which is minus I. Or you could say, well, what is 1 over I? It's what you have to multiply by I to get 1. Well, minus I times I is 1.
Or it's just I to the negative 1,
Right.
which is the same as I to the third, which is the same as negative I.
You could do this as well, right? Okay, so there's a lot of different ways to see it. Yeah? So I is very versatile. Okay, so that means we can put this I on the bottom, make it a 1 over 2i, but when we do that, we pick up a minus sign. You're allowed to do that. So this is minus 1 over 2i e to the I z minus e to the minus I z. But now this is exactly minus sign. So over 2i to the e to the I z minus e to the minus I z, but there's an extra minus sign, so this is minus sine z. So sure enough, it works.
Fantastic.
So that suggests this might be the right definition. Now let's, just for fun, let's see if we can't check the sine squared cosine squared identity. Maybe it worked, maybe it doesn't. Let's see. Let's check it. So we have to square this. So let's see here. You get e to the 2iz plus, well now it'll be 2 times e to the iz times e to the minus iz.
2.
It's just 2, right? These things, when you multiply them, you just get 1, because the exponents add to 0. So you just get a 2, plus e to the minus 2iz over 4, plus, and we do this one, you get e to the 2iz. Now it's minus 2, and then it's plus e to the minus 2iz. Again, all over, well now it's over minus 4. Okay, so we can make that minus go over there. So let's see, e to the 2iz minus e to the 2iz, those go away. 2 minus negative 2, so that's positive 4. And then e to the minus 2iz plus minus e to the minus 2iz, those cancel. So it's just 4 over 4, which is 1. So it works. Good. Okay. So this is right. Okay, this is the right definition. Okay. Now, things do get a little weird. Not everything is going to work exactly the same way as you're used to. When you're working just over the real numbers, sine and cosine are terribly restricted in their output. Right? Remember, they have to live between plus and minus 1. They can't go anywhere. It's going to turn out that sine and cosine are, over the complex numbers, unbounded. They can get as big as you want them to. And that's really easy to see. Let's say we look at cosine just of, say, yi. So, if we plug this into the formula, this is e to the I times yi. So that's just e to the, you put in yi.
Minus y.
You get minus y. Okay, and then a plus e to the, well, it should be minus y with another minus, so just positive y. And then this is over 2. Ah, well now this is actually a real function. Right? There's no imaginary numbers on the right side anymore. What I mean, the output is real. Okay, so what's the range of this function over here? Not all real numbers, because for instance, what can't you get from it?
0.
Certainly can't get 0, you also can't get anything negative. Right? E to the minus y and e to the y. E to the y looks like this. E to the minus y. Ugh. Okay, it's looking like that. And they meet here. 1. Y is 0. Okay, I'm actually drawing this not in the right direction. Right? I'm calling that my x-axis and that's the y or something. This is not so important. Okay, you put in 0 for y. Okay, so when you add these two things up, okay, they certainly can't ever get negative. Okay, even when you divide by 2. But, so they can never get, I mean actually what's kind of the lowest they're going to get? Well, it kind of looks like maybe 1/2 might be as small as they can possibly get. And what's as big as they can get? Well, there's really no limit, right? On this side, or on that side, right? They can go up and you add a little bit to it, but it just makes it bigger. So cosine of yi goes along, I mean the answer to this is always on the real axis. And it's supposed to be a map onto the complex plane, but it actually just ends up on the real axis. And you can have it go out as far as you want on the real axis. So if you talk in terms of the norm, right, being the size of the vector, this is unbounded. You can get as big as you want. Which is a stark contrast to the real version of cosine, right? Where the real version of cosine, if you did cosine of x, this always lived between 0 and 1. Okay, so there's a substantial difference between these two functions. And we've only done the yi bit, right? Generally speaking, z could be x plus iy, so there could be a lot more interesting things going on. It's not like the values of these are always going to be real. It's just when it's cosine of yi that it's always real. Okay, and of course, similar thing holds for sine. Right? Oh, you guys are cool? Is that Kylie's shirt? You dog.
Say that again.
Okay. What do I want to do now? Let's see. Oh, wow. Oh, I do want to mention that. I forgot to mention. There's one other thing. We showed that the derivatives are the right derivatives. We showed that they satisfy the most important trig function there is, or formula there is. There's one other aspect of sine cosine we didn't talk about, was what kind of special functions are they? They do this.
Periodic.
They're periodic functions, right? Just repeat. And what's the period? 2 pi. That one's every 2 pi. Are these things still periodic? Okay, well, over the real numbers, we knew exactly what we meant by periodic, right? There was a certain amount of time, and if you add that certain amount of time, same thing happened. Okay, so what do we mean for the complexes? All right, so there we're talking about angles. So if I take my z up here and I replace, well, let's just look at e to the z for a second. What happens if I look at e to the z versus e to the z plus 2 pi I? Well, let's see. You can break this up as e to the z times e to the 2 pi I. And what is e to the 2 pi I? Well, remember, e to the I theta lives on the unit circle and it has angle theta. So if angle is 2 pi, then see 2 pi is over here. It's just 1, right? That's the value over in the unit circle right there. 1. So this is e to the z times 1. It's just e to the z. So these are actually equal. So the period of e to the z is 2 pi. That's the way we'll say it. Or you could say 2 pi I. But I usually stick with this 2 pi. Now, if you look at the definitions of cosine and sine, if you replace the z here with a z plus 2 pi, then you're exactly in this situation down here. So if you look at cosine of z, which is e to the iz plus e to the minus iz over 2. And if we look at now cosine of z plus 2 pi, which is supposed to be the period, this is e to the iz plus 2 pi I. For the first component, you replace z with z plus 2 pi. The I distributes. Plus e to the minus iz plus minus 2 pi I over 2. Again, this 2 pi I business is not going to hurt anything. It's not going to change the value of e because e is periodic. Period 2 pi I. So this is exactly cosine of z again. So the fact that e to the z has period 2 pi I makes cosine of z and sine of z have period 2 pi, which is what we wanted. Any questions about this? Okay. Let's go back to the complex logarithm, which we talked about at the end of last class. So we gave a definition. We said that if you have a complex number z, then the log of z is given by the natural log of r, where r, and here z is written as re to the I theta, polar form. So log z is just the natural log of r. That gives you the real part. And the imaginary part is I theta, where theta is the principal argument of z plus 2 pi I, right? You're allowed any theta in here that satisfies this. Right? Oh, there's a k missing. Oh, actually, I don't need the I because I get hit by that. So arg of z plus 2 pi k. Okay, so this is not actually a function. This is a multi-valued function. So then we said this is really annoying not having a function. So let's make it a function by just choosing one special angle to go here. And we said, okay, the special angle will be when k is 0, so you just take the argument of z. So log of z with a capital L is equal to the natural logarithm of r plus I times the principal argument of z. You look confused.
Are those two things the same thing?
What's the difference between these? The difference is here I have the argument of z, but I'm also allowed, right, for any integer. I can take any of these thetas, right? K could be 0, k could be 1, k could be minus 1.
So that is what they want on top.
That's right. So this is not actually a function because for one z, I actually get more than one theta. Right? I get an infinite number of thetas. Here, this is actually a function because I'm specifically choosing this one argument, right? The principal argument of z. So let's recall an example. I think we did this last time. Let's look at the log of minus 1, which you're not supposed to be able to do. So the first thing is that this is the natural logarithm of r. So r here is the norm of z. Well, z here is minus 1, so what's the norm of minus 1? 1. So this is just log of 1 plus I times the argument of minus 1. Okay, so where does minus 1 live? Minus 1 goes over here.
Pi.
Argument is pi. I pi plus 2k pi. Okay, because you have to, 2 pi k, whatever you like. You have to include all these possible, right? Because it's not just pi over here. It's also 3 pi and 5 pi and 7 pi and also minus pi and minus 3 pi.
So R is the norm of Z.
Yep. R is whenever you write something in polar form, the R is always the norm.
But if you put capital L of that now, then it will be just I pi
Yeah.
without the two.
Oh,
Okay.
before I write this, of course, what's ln of 1? Yeah, it's 0. Gotcha. Yeah, right? Natural log of 1. This is saying e to what power is 1? Of course, 0. Okay, so this is actually just I times pi plus 2k pi, which is I times 2k plus 1 pi. Fine. But if we put capital L, then we don't look at any of the k's for non-zero k. We just take the k where it's 0. So this should just become, I like writing the I last, just pi I. Now the log should mean what it does over the reals in that it's an inverse for the exponential function. So it should be that if I raise e to the pi I get negative 1. Of course it does, right? What does this mean? When you put an e to the I theta, it just means you go on the unit circle and look at that angle theta. Well, the same angle theta over here, pi, right? So there's minus 1. Of course, it's true. Okay, so this is an inverse for the exponential function. So that means it's the right definition of logarithm. But something funky is going to happen. Now, to see how this funky thing is happening, you have to remember an important formula from real logarithm theory, which is what happens when you take the log of a product.
It's a log of x plus.
Right? The log of a product is the sum of the logs. So this is log of x plus log of y. Okay, so let's try over here. Let's use our capital L's because, I mean, this is really annoying having to have all these 2k pi's floating around, right? So let's just use our capital L. So let's look at the log of 1. Now the log of 1 is, well, it's ln of the norm of 1, which is still 1, plus I times the argument of 1. 1 is sitting over here on the x-axis, right? That's just angle 0. So it's actually just I times 0. And we know ln of 1 is 0 and I times 0 is 0, so it's actually just 0. Okay, good. That's the way it's supposed to be, right? When you do ln of 1, you get 0. Log of 1 should be 0. Fine. What if you do, instead, log of minus 1 times minus 1? Well, I actually haven't done anything different, right? Minus 1 times minus 1 is still 1. So this is actually the same thing. So this has got to be 0 also. But we know that we can break up a logarithm of a product as a log of the sum. So this is log of minus 1 plus log of minus 1. Ah, but we've computed log of minus 1. It's pi I. So this is pi I plus pi I, which of course is 2 pi I, which is decidedly not equal to 0. Did we do something wrong? Well, what's the only thing we did that we didn't prove?
Properties of logs.
We didn't prove the properties of logs, right? We broke this up here as product, log of a product is the product of the sum of the logs, but we don't have that. In fact, this basically says that doesn't work. Okay. Now, these are really close in one sense. E to the 0 equals e to the 2 pi I. So how can we make it work? Well, if we weren't working with capital L, if we were just working with little l, then when we did log of 1, this actually would have been 0 plus 2 pi k I. Right? You would have infer, and k would run. And if you'd have done log of minus 1, well, we know what that is. It's I 2k plus 1 pi. Right? And then you'd have 2 of those. So you'd end up just, well, these are all the odd multiples of pi. When you multiply by 2, you get all the even multiples of pi. So if you have 2 of them added together, you'd end up getting, well, all the even multiples of pi. We don't need the 0 on here. So if you use little l, which is not actually a function, it's a multi-valued function, then the formula for logarithms does work. So it's why we can't just say, well, we'll only, what's one of the reasons we can't just, well, just work with big L. Because there are some little technical problems that show. It also says, before you use any property about these functions that you know is true for the reals, you have to check it for the complexes. It's something, I mean, this is not where you'd expect things to break down, right? And this is like such a basic formula from logarithms. You wouldn't expect it to break down here, and yet it does. So we better check, for instance, well, what do you think the derivative should be for the logarithm?
1 over z.
Yeah, that's what it should be. But now we're not so sure. So we're gonna try to check it. All right. So the next thing is find the derivative of logs. So as usual, because we're working with log, it's more convenient if we write our z in polar form. So we'll write z as re to the I theta. So to compute the logarithm, well, we go back to the definition of the derivative. So here, since we're doing it in polar form, the way we're going to do it is we're going to look at a change as delta r goes to 0. And change the radius. And then we'll do I should actually look at my notes, make sure if you don't start it off right, you're toast. Now's the time to stop and start it out right. Oh yeah, that's right. That's right. Okay, so yeah, I think. Oh, I remember now. I didn't want to explain it that way. Yeah. Okay. So let's not write it like this. Okay. Let's write our log in the UV polar form. So we know there must be some way to write it in this form. And so if we do that, then as we take delta r to 0, the derivative looks like this. Doing r plus delta r, comma theta, and then we subtract r comma theta. Okay, so this is the real part. And then we have to change the imaginary part. So plus I times v of r plus delta r theta minus v of r theta, and we divide by delta r. Happy? Good. Okay, now this is actually going to look fairly familiar, because we actually did this computation to compute the Cauchy-Riemann polar form. So what happened? Well, we broke this up into two different fractions. One with the u's, one with the v's. And then we noticed, well, we gave an argument that each of the individual limits existed, so you could break it up and pull out the I. And when you do that, what happens? Well, this is actually the partial derivative of u with respect to r. So this ends up being the partial of u with respect to r. And this over here is the partial of v with respect to r. Times I. But we're missing something. That's right. What are we missing? Well, when we did this before, we actually had an extra term on the bottom. What's the extra term on the bottom? The extra term on the bottom is an e to the I theta. Now, why do you have that? Well, as you as you change the point, right, you need to take into account the angle. And that's what this thing on the bottom is doing. So we have all this, but this e to the I theta, which is not dependent on the delta r, that can come out. So you get 1 over e to the I theta. Okay, so actually this, notice what we're doing here. I mean, this is just, I mean, this has nothing to do with log right now. Okay, this is something, I mean, we already did this once before. All right. Now, what would be nice then is if we could somehow do it this UR and this VR. VRR, yes. What they is. I am imaginary? No, I is imaginary. Okay. Right. Well, let's go back to our definition for log z. Log z equals ln of r plus I theta. And so this is actually your u of r theta. And this is your v of r theta. So we can actually compute what UR and VR are. UR is just the derivative with respect to r of ln of r. And that we know is 1 over r. That's just the real version. VR plus the derivative of theta with respect to r. What's the derivative of theta with respect to r? 0. Oh, that's nice. If we plug these in, what happens? Well, the UR becomes 1 over r, and the VR is 0, so that whole term goes away. So you're just left with 1 over r e to the I theta. But what is r e to the I theta?
That's polar form.
That's the polar form of z, right? That's
So
what
it's
z is.
just-
This is 1 over z. Ah. Cool. It did work. So the derivative of log z is 1 over z. By the way, this actually is, we're missing a step somehow. What are we missing? Well, we're saying if, what we've said is if the derivative exists, then it's 1 over z. We actually didn't prove that it's analytic. Okay, well, how can we prove it? Well, we need to find all the partials. Well, first we'll check the u's. ln of r, yeah, that's definitely a continuous function. Theta, definitely a continuous function. Okay, UR and VR, those are fine, except it's 0 when r is 0. But if r is 0, then that means z is 0. And this function you're not allowed to define on 0 anyway. Okay, so it's analytic everywhere. I mean, these are continuous everywhere except 0. Now we need the Cauchy-Riemann equations. Okay, well we have UR and VR. We need U theta and V theta. Well, U theta is, well, that's just 0. There's no thetas. And V theta is just 1. These are certainly continuous functions. So we're fine up to the Cauchy-Riemann equation. So what did Cauchy-Riemann say? Well, for polar form, UR should be 1 over r v theta, right? Is that right? So UR is 1 over r times v theta. Yeah, sure. And VR should be negative 1 over r times u theta. And, well, those are both 0, so there's nothing bad that can happen.
Perfect.
Cool. So the Cauchy-Riemann equation is also really, it is an analytic function, except it's 0. So log z is analytic, except at 0, where it's not defined. And the derivative of log z is 1 over c. Cool. So we're basically, we're doing what you always do in math. Is you develop some new subject and then you try to reduce it to one you already know how to do. So we know how to do a lot of stuff with real numbers and real functions, and so we're just trying to write down all these analogs into the complex world and see if they have the same properties. And sometimes they do. Well, so over here, sometimes they don't. Okay. Are there any questions about the logarithm? Do you understand how you compute it? As far as you just need to find the norm to get the r, and then take that, and then you need to find the argument. So, for instance, here we'll do one quick example to make sure everybody's on the same page. Let's say you want to do log of 1 plus I. So to do what you want to do is put it into polar form. Because once you get polar form, you can just read everything off. So what's the polar form of 1 plus I? Alright, so you need the norm. What's the norm? 2. E to the I. Okay, what's the argument? Let's see.
Pi over 4.
Yeah, right, there's 1 plus I. So pi over 4.
Because it's tan and you want to be
If you like. Yeah, arctan of 1.
arctan of
Or you just notice there's
the
45,
sine
45
equals-
right triangle. Lots of ways of seeing it in any case, right? This is the pi over 4 angle. And that's 1 plus I. So there's your argument. I pi over 4. So the log is the natural logarithm of root 2 plus I pi over 4. And if you wanted the lowercase log, then it would be plus log of 1 plus I is ln root 2 plus I pi over 4 plus 2k pi. And there's the multi-valued version of log. Not so hideous. Okay, well, I think that's enough for today. So tomorrow we'll start with complex powers. So we'll do it in a few steps. We'll start with integer powers, which is very easy. Then we'll go to rational powers, which is only slightly more complicated. And then we'll go to non-rational powers. And that's when it gets fun. I don't think that will take us all tomorrow. Well, only 50 minutes tomorrow. So it might. Actually, it probably will. On Thursday, I have 2 ideas as to what we might do, and I'm inclined to suggest one. And I'll tell you both. I'll focus on one. Number 1 is that we can push on to the next section, which is when things start to get really interesting. That's when we start contours and integrals, line integrals, and so forth. Or the downside of starting it on Thursday is we start it on Thursday and then you immediately go home for the weekend. You don't think about it until Tuesday, perhaps, because you're working on other stuff. The alternative is that we use Thursday as a day to sort of kind of catch up and review, just kind of go over some things again, maybe work a few exercises that you've been struggling with or something. And that way we're all fresh, and then on Tuesday we can really get into it and have a full week of thinking about it. Are there any objections to the second method? No?
Is attendance mandatory?
Attendance is not mandatory to any class. And this will be the last day Christina joins us. Yeah.
Tomorrow.
So okay, so if there's no objections, then okay, so tomorrow we'll just try to recover. So what that means though is that you need to be prepared to ask me questions about either specific problems or material that you're not quite getting.
Can we just have a group homework session on Thursday?
I mean, we can certainly do that as part of it.